So having studied the forward algorithm, we will now study something known as the backward algorithm for HMMs. This is the fourth problem that we are seeing in HMM. What we're trying to predict is to find out the, the probability of sequence x of small t plus 1 through t, given that the state at time small t is I, right? So this is denoted by beta sub t of I. Again, to ensure that the definition is very clear, beta sub t of I is the probability of sequence xt plus 1 till t. So you observe a state z equal to I and you have a model parameter theta. Condition on that, you want to see the probability of observing the data from the next timestamp. So the important thing to note here is to again try to write the induction step or the recurrence relation of beta t of I in terms of beta t plus 1 of j. Now this has to be done in a similar fashion, or the learnings, the insights, or the way in which we're going to do this, the backward algorithm in induction and recurrence is fairly similar to the way we did for the forwards algorithm, in which we were doing for the variable alpha t. The only difference is in the direction in which the recurrence or the induction would be applied. So there we were defining alpha t plus 1 in terms of alpha t, but for the backward algorithm we're going to be defining beta t of I in terms of beta t plus 1 of j. So we are moving backwards from capital 3 to 1. So one thing you want to now do is to take a minute off and try to write the relationship between beta t of I and beta t plus 1 of j. So where I and j both are going to be one of the k states, right? So assuming you took a minute and you wrote down the formulation yourself, so we can write beta t of I is defined to be probability of the observation sequence t plus 1 through t given zt equal to I. Now what we're going to write is from z equal to I, you could go to zt plus 1 equal to 1 to till capital K. So it can go to any of the 1 to 1 of k cases, right? And once you've reached any of those k cases, let's assume that you are in the jth state, right? So you are z of t plus 1 is the jth state. Now you can again define beta t plus 1 of j, which will include the probability of x of the observation sequence x of t plus 2 till capital T given the zt equal to j, right? So what we'll try to do is to write down beta t of I in terms of beta t plus 1 of j. So let's look at the different paths. So you were at z equal to I. You could observe you could make a transition from state I to state 1, which is shown in red. So that is going to be involving the transition probability AI1, and at time t plus 1 you could observe, you're observing the observed variable x of t plus 1, and if you multiply this with the probability of observing the sequence x of t plus 2 till capital T, given that x of t plus 1 equal to 1. So this is one such path that you could take, going from x of t equal to I to x of t plus 1 equal to 1. You can similarly repeat this for the next path, which I've shown in yellow, and similarly for the final kth path shown in pink. So you have k such paths. Now the important thing, or the way in which the recurrence will be defined, is to try to look at the first term in each of these sums. p of x of t plus 2 till capital T given zt plus 1 equal to 1, 2, 3, j till k, right? So isn't this the same definition as what we've defined for beta t of I, but replacing t with t plus 1 and I with j, right? So pause for a minute and ensure that you understand what I've just discussed. So effectively what I'm saying is the induction step is beta t of I is summation over j running from 1 through k of beta t plus 1 j. So basically this is saying that the probability of observing sequence from time t plus 1 till capital T can be written as the sum of all the paths starting from any state, from the state j, but you need to move from state I to j. So there is a transition probability multiplication of aij, and you also need to observe xt plus 1 given that you are in the jth state. So that term is phi of j xt plus 1, and you're summing it over all the paths, which is summing over j equal to 1 till k. We also need to, so we'll be running this induction. So if you see, we're defining beta t in terms of beta t plus 1. All we need to do to define all of the beta parameters is to define the beta capital T, which is the beta for the last time step. And then we can run a loop going backwards from t minus 1 till 1. And we can apply this recurrence relation. We arbitrarily define beta at the last timestamp, beta capital T of I equal to be 1 for all I. So with these two steps, we have everything required to compute beta for any examples given to us. Let's take a concrete example. This is the same set of observations we've been seeing thus far, which we used for the forward algorithm computation. Now we'll be using for the backward algorithm computation. You have x equal to h, and you want to find beta 1, beta 2, beta 3. The first step is to initialize the beta capital T for all the states. So you have two states, biased and fair, and the time capital T is 3 because we have 3 observations. So once we have done the initialization, we can then define the recurrence relation. First, we need to find beta 2 of B and beta 2 of F. So where we're going to define beta 2 of B to be sum over J, so sum over all the possible transition path from between different states it could have taken, of beta 3 of J times the transition from the state B to state J, where J is either B or F, times the emission from the state J of observing H, right, where H is x of t plus 1 or x of 3. So this is going to be, you just plug in the value of J to be B and F. This will be beta 3 of B times the transition from B to B times phi B of H plus beta 3 of F transition from B to F multiplied by the emission of H from the failed state. So if there is any confusion, I would request you to draw the Strelitz diagram again. You're defining the relationship between beta t of I to beta t plus 1 of J. And we observed in the example that we'd seen previously that we need to draw all the possible paths. And then we can just define this term, which is the definition of x of t plus x of t equal to I, and we can define this x of t plus 1 probability of x of t plus 1 through t given zt equal to y. And we basically just break it down into the different paths you could take at time t plus 1. Similarly, we can calculate beta 2 of f. While I'm just breezing through this slide, I would request you to pause, do all the calculations and verify that you're getting what is being written on the slides. So beta 2 of f can again be written in terms of beta 3 of b transition from f to b times phi b of h plus beta 3 of f times the transition from f to f times the emission of h from f. So this turns out to be 0.52. You might again see that individual beta i's will not sum to 1. So if you want to again get the conditional probabilities, you'll have to do the normalization. Similarly, you can calculate beta 1 of b and beta 1 of f. So where again beta 1 of b will be defined in terms of beta 2 of b times the transition from b to b times the emission of h from b plus the beta 2 of f times the transition from b to f times emission of h from f. This turns out to be 0.4544, and similarly you can calculate beta 1 of f. So it's always a good exercise to try to calculate these things on your own. Having discussed the backwards algorithm, we'll now be studying the next algorithm or the next problem. So the next problem is, can you determine the optimal sequence of states given the model theta, where theta consists of pi, a and phi, and the observations, right? So this problem is different from the previous problems, but this problem can heavily leverage the previous two forwards and the backward algorithm that we have discussed thus far. So one important issue of contention that you might see here is how to define the word optimality, right? What is the definition of optimal sequence of states? So the first definition that we'll see is a simple definition, so which does not consider the word sequence very seriously here. So the definition is that you choose at each time point t the state zt which is individually most likely to occur, right? So I would request you to again think for a minute and write what you understand of this definition. What would zt look like, or is the estimate of zt look like? So as per this definition, z bar would be given as argmax of probability of z1 given the entire sequence x1 through capital T, and this is maximized over z1. Similarly, for any arbitrary t, it is going to be zt bar will be argmax of the probability of observing a probability of that state z at time t given the entire observation sequence, and you're trying to maximize it over the observation sequence. If you would have noticed, I've written something known as MPM over here. So this MPM refers to what is the quantity that we're trying to estimate. So what we're trying to estimate is a sequence of marginally most probable states. So if you notice that it is a sequence of marginally most probable. So there is you see a marginal here state in terms of the observation, and you see the most probable, which is defined in terms of this argmax operator, and there is a sequence of each of these marginally most probable states, right? To think about how to go ahead and solve this, we'll be defining, similar to parameter alpha and beta that we have defined earlier, we'll be now defining a parameter gamma. So we'll define gamma t of I to be the probability of at the tth time step that we are in state I given the entire observation sequence, right? So I would request you to now pause for a minute and think in terms of, can you break down this expression of gamma t of I into the quantities that you already know. So you already know the definition of alpha t of I and beta t of I. If you can somehow break down this formula in terms of alpha and beta, you have almost solved the problem then. So what I'm going to do is to firstly change the equality to a proportional sign, and this is ignoring all the normalization constants for now. We are going to break down the calculation of z of t equal to I given x1 through t into two parts. The first is the conditional z equal to I given x of 1 through small t. So all of these t's are small now. And if thus far we've only considered the sequence 1 through small t, but the overall sequence given to us is 1 through capital T, right? So there needs to be the other part of the sequence which we also need to consider. So that comes into this expression. The second part of this expression is, now you've observed some data x1 through x small t. You've reached the state z equal to I. And what I'm now saying is that given these two, given that you have reached z equal to I and you've observed z1 through t, what is the probability of generating, or what is the probability of the remaining t plus 1 through capital T data or the observations, right? And there is a proportional sign. You can apply Bayes' rule to figure out the normalization constant over here. Now, considering this term, the second term or the term on the right, this is the conditional on a conditional of x of the sequence xt plus 1 till capital T given zt equal to I and x of 1 through t. Now if you know zt equal to I, does x t plus 1 through t depend on x 1 to t? No, so they are independent terms. You could of course look at conditional independence rules or the influence of certain nodes or Markov blanket to understand this property better. I'm not going to delve into any of those concepts. All you need to understand is that once you've observed z equal to I, all of the previous or all of the observations from x1 through t are not important. So we can then write down this expression to be proportional to zt equal to 1, z small t equal to 1 given the partial observation sequence from 1 through capital T, small t, multiplied by the probability of seeing the observation sequence from t plus 1 through t given zt equal to I. So this can now be seen to be proportional to alpha t of I multiplied by beta t of I. So if there is any confusion, you should go back and look at the definitions. You might notice that the definition of alpha t of I is not exactly this left hand side term. The definition of alpha t of I included a joint probability instead of the conditional probability that we see over here. But since we're talking about only proportionalities, we don't really care at this point. We can figure out the normalization constant later, right? The normalization constant is just the summation over all the i's in this case. So we can then write gamma t of I to be alpha t I multiplied by beta t I, and the denominator is just the summation over all the possible i's. So another thing which I forgot to mention is that the optimal sequence of states, or MPM, is also known as the forward-backward algorithm. Now, given that the computation is in terms of alpha and beta, I hope you understand that why it is called forward and backward algorithm. For computing the betas, you need to take a backward path. For computing the alphas, you need to take a forward path. Let's do a quick exercise. Again, we'll use the same dataset that we've been using thus far. And an observation same set of parameters theta, same set of observation x equal to h, comma h, comma h. We want to find out the smooth set of states using the NPM criteria. So all we need to do is to define gamma t of b and f for all the different times, right? And then we can just do an argmax to over gamma t of b and f to figure out which of them leads to most, so which of them leads to the state which is most likely at that point of time, right? So the first thing we want to do is to compute gamma 1 of b. I'd request you to compute gamma 1 of b and gamma 1 of f. Gamma 1 of b can be written as alpha 1b times beta 1b, and the denominator would include both the b and the f terms. Thus it would be alpha 1b times beta 1b plus alpha 1f times beta 1f. I have just plugged in the numbers I've calculated thus far, and this number turns out to be 0.77. Now it should be noted at this point that gamma t is already normalized. So without even having to do all the calculations, I can just write gamma 1 of f as 1 minus gamma 1 of b, given that we're only dealing with a two-state problem. Thus, gamma 1 of f is 0.23. So all this is saying is that at time step t equal to 1, it is much more likely to have z1 equal to b if the observation sequence is h, 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 and the theta is given. We've just shown that since gamma 1 of b is greater than gamma 1 of f, so the argmax over the gamma 1 over the different states is b. And if we keep on doing this observations or this algorithm for t equal to 2 and t equal to 3, which means that effectively we're computing z hat to be argmax over the state I or gamma 1 of I, comma argmax over I over gamma 2 of I, and so on and so forth. We'll end up with the NPM sequence of states to be biased, biased, and biased, right? So this again sort of makes sense given the fact that we have observed 3 H's, and the fact that the likelihood of the probability of seeing heads is much more from the biased coin, right? Could you think of any other definition of optimality? So we have seen one definition of optimality in terms of maximally, which is sequence of maximally probable states or maximum marginal probability states, right? Could you think of some other definition? The next definition of optimality that we'll be seeing is the map or maximum a posteriori, which is to choose the most probable sequence of states. There is a very big distinction between map and NPM. First, let's now try to understand what is map. So now we are saying that we're trying to learn Z star such that it maximizes the probability of a sequence of states given the observations. So maximizes the sequence of states over this conditional, right? Now let's take a trivial example, not in the coin toss example that we've been seeing thus far, and observe how a map and NPM can be different. Let's look at this joint probability table for two timestamps. So Z1 equal to 1 and Z1 equal to 2, you could imagine being Z1 equal to B and Z1 equal to F. And similarly, Z2 equal to 1 and Z2 equal to 2, you could imagine being Z2 equal to B and Z2 equal to F. So you have 4 entries in this joint probability table. You could also compute then the marginals, right? So the marginal for Z1 equal to 2 is 0.6 and Z1 equal to 1 is 0.4. Similarly, the marginal for Z2 equal to 1 is 0.34 and the marginal for Z2 equal to 2 is 0.66. Now let's plug in the definition of MPM first. So MPM will choose a sequence of marginally most probable states, right? So sequence means sequence of marginally most probable states means that for time t equal to 1, we look at the marginal, we see what is most likely. So if we look at time t equal to 1, the most likely is the second state, since 0.6 is greater than 0.4. If we look at timestamp t equal to 2, we again perform this independent computation. Which is more likely, 0.34 or 0.66? So since 0.66 is greater, therefore the second state, or the state at time t equal to 2, as per MPM definition, is Z2 equal to 2, right? So thus Z hat according to MPM in this case is Z1 equal to 2 and Z2 equal to 2. But think for a moment and tell me what is the map solution here. So if you look at the definition of map again, map was choose the most probable sequence of states. So here the sequence is important. You cannot element wise or time wise choose the most probable state. But to choose, in this case, the Z1 and Z2 whose joint probability is the highest, right? So in this case, Z1 equal to 1 and Z2 equal to 2. If you see where my cursor is, that's the joint sequence of states which is most likely, right? So thus you should see that in the case of MPM, the most optimal set of states was Z1 equal to 2 and Z2 equal to 2. But in case of map, the most optimal set of states is Z1 equal to 1 and Z2 equal to 2. So let's now try to understand the algorithm behind map. So it's another dynamic programming algorithm. We have seen thus far the forward algorithm, backward algorithm, and the forward-backward algorithm. This is yet another dynamic programming based algorithm, and it's called the Viterbi algorithm. We'll be defining yet another variable, delta t, delta sub small t of I, which we're going to say is the best score or the highest probability along a single path at time t, which accounts for the first t observation and ends in zt equal to I. So it's a complicated sounding thing. Let's break it down and look at the different colors. First, we want to see that we want to end in state zt equal to I, right? So we are talking about this joint conditional on the parameters. So the zt equal to I is a part of this formulation. You want to see a single path at time t. So single path going from z1 to z of t minus 1. Right? So this path basically would mean z1 equal to biased or fair one of them, z2 equal to biased or fair one of them, and so on and so forth till time t minus 1. And you also want to account for the first small t observations. So that's encoded in the red color, right? So that's the definition, that you want to be encoding you want to find out the path, and you want to be finding out the score of that path, which ends up in the state zt equal to I, and it accounts for the first two observations, right? So think of it as the goal of this is to first figure out a path and then figure out the score of that path, or vice versa. Now, it's important to look at the differences between alpha t of I and delta t of I. So we have just defined delta t of I as the expression you can see on the top, and alpha t of I we have already defined above. So one thing which they very clearly have in common is that both of them end up in state zt equal to I, right? So in the first delta t of I case also, you see that you end up in zt equal to I. Similarly, you end up in z equal to I for in the alpha variable definition. And both of them are also talking about the observations, right? Accounting for the first two observations. But there is a very significant difference between them, because delta t is focusing on the most likely sequence, or it's a score of a sequence, whereas for alpha you're focusing only just on a single state at time t, right? So as usual, we want to do a derivation of the relationship between delta t of I and delta t plus 1 of j, where again I and j could be states from 1 through k. So I would request you to pause the video for a minute, think for a minute, and try to figure out the relation between them. To help you to think about the relation, I have just drawn a trellis diagram here, which has been simplified for the two states problem, where the two states are biased or fair, let's say. So the important thing again here is to try to break down the definition in terms of t and t plus 1, and then seeing what is observed and in terms of these definition of the variables. So the first step I'm going to tell is right here is I'm showing here that I've calculated the delta t for each of the k states, and I also know that there is a transition probability associated with going from each of the k to each of the next k states. And I've just redrawn this diagram on the top. We know that we could reach zt plus 1 equal to j, where j is 1 and 2 over here, from any of the I, where I is varying from 1 to 2 here, in general 1 to k, via transition with the probability aij, right? And once we have reached zt plus 1 equal to j, then the probability of observing x of t plus 1 is phi j of xt plus 1. So with this, we have everything which is required to define delta t plus 1 in terms of delta t, right? So it's important to again try to work this out on your own. Look at the definition of delta t of I and then try to see what it meant. So delta t of I was maximum score along a path z1 through zt minus 1, which ends up in state I and accounts for the observation t, right? Now for delta t plus 1 of j, what we're saying is we're ending up in a state j and accounting for observation x1 to xt and xt plus 1, small t plus 1, right? And we're then trying to maximize the possible sequence of states. So the only thing you need to see is that going from I to j, you've already calculated delta t of I, right? So all we now need to do is to find out the path from I to j, which maximizes the quantity delta t of I times aij. right? Because the term on the right for observing or for the emission of xt plus 1, where xt plus 1 in our case could be either a head or a tail, is given by phi j, time phi j function of xt plus 1, right? So what we want to say here is that you want to choose which path amongst which previous state and the transition probability combination should you choose, so that you're maximizing the sequence of states, right, which account for the observations and end up in a state J. So thus we can write this recurrence relation. I would request you to again stop for a minute or two in case this is unclear, because without a thorough understanding of this definition, it will be difficult to work through an example. Okay, assuming you have now understood this concept, what we want to do now is to, while this term is telling us that what is the maximum score, but our ultimate aim, if you look at the definition of delta t is just a score. Does it tell the most likely sequence of states? No. So what we want to do is to, while we taking a forward pass from small t equal to 1 to capital T, we keep on storing delta t for each of the individual states, but we also need to store psi of t for each state j, which tells us the argument I in this definition, which had maximized the above equation, right? So for example, at this time instance, what was the most recommended path? Was it a biased state or a fair state, ending up in either a biased state or a fair state as per delta t plus 1 of j, right? And accounting for the observations. So that we store in psi t of j. So thus we now look at the different steps of the algorithm. We have to define delta 1 of I, right? So which means for the first time instance. Could you think for a minute and tell what this definition could be? So to understand this, let's go back to the definition of delta t of I. So that's a maximum score of over a sequence of states z1 through zt minus 1 of observing probability of the sequence of states ending up in sequence and state I and the observations, right? So at t equal to 1, can we write this as the probability of ending up in state I being pi of I, and the observation sequence that you're seeing is only x of 1, right? So in the ith state, the probability of seeing x1 is phi I function over x1, right? And we arbitrarily define phi 1 of I equal to 0. We are not going to be making use of phi 1 of I anyway. So the next step is, as we've been doing for the forward algorithm, the backward algorithm, the forward backward, is to just apply the recursion step, right? So the recursion step is, firstly we iterate over the variable time t from 2 to capital T, and then over each state j. So we could, given a state I, we could go to a state j, right? So we defined delta t of j in terms of delta t minus 1 of I, and you iterate over all the possible i's to obtain the maximum score of ending up in state j and which is consistent with the set of observations, right? So we define this as we've defined earlier as delta t minus 1 of I times aij, and you maximize this quantity over all the possible previous i's you could have come from, and that maximized quantity is then multiplied by the emission from state j, phi j, of observing the xth observation, right? And the psi t of j is just the argmax over the first term in this expression, which is just telling what state I maximized this quantity. Then we go on to the termination stage. In termination, all we need to do is to just maximize, or P star is just the maximum score you could obtain of, or the score of the most likely sequence of states, and that is just delta capital T of I being maximized over the different states I going from 1 through k, and ZT star, Z capital T star, is telling us the state which maximized the above quantity, right? And the important step then is to do backtracking as you would do in any DP algorithm. So you go from small t, from capital T minus 1 through 1, and you compute zt star, z small t star, to be psi t plus 1 of z star t plus 1. So this is just purely backtracking. You're trying to figure out the sequence of state which should have been, the state which should be chosen to maximize or to reach to the overall maximum score P star, right? So we should be now looking at an algorithm to understand this better. We have theta equal to pi a phi, and the set of observations is the same as we've been seeing thus far, h comma h comma h. We want to determine the sequence of states as per the map rule z star. So we are given pi a and phi as we've seen thus far. So if you go through the steps, the first thing we need to do is to calculate delta 1 of I for each state. We have two states here, bias and fair. Could you take a minute and calculate delta 1 of bias and delta 1 of fair? So delta 1 of bias is just pi of bias times the emission of h from the bias state, which is pi bias times phi bias of h, which is 0.42, and delta 1 of fair is pi of fair into phi fair of h, which is 0.2, right? And we are anyway arbitrarily just defined psi 1 of bias and psi 1 of fair to be 0, so they don't anyway come into the picture. Now the important step is the recurrence step. Can you calculate delta 2 of bias now? I would request you to pause the video for a minute and work it out yourself, and then we can see the solution. Okay, for delta 2 of bias, we'll be looking at the maximum amongst these two quantities, which is starting from state fair and observing x1, and then taking a transition from fair to bias, versus starting from state z1 equal to bias and then making a transition from bias to bias. And of course, we, for the first state, we also do a transition we also do an emission from bias to hedge. So both the emission from the first time step is, and the observation, sorry, so the observation is the emission, and being in state bias is taken care of delta 1 bias, and we multiply that with the transition probability. So we have these two terms which are basically now two competing first states which would have been chosen, but we want to maximize now what happens at the next time step. So what is the most probable sequence of path reaching to the state z2 equal to bias, right? Is z1 equal to fair, or is z1 equal to bias, right? So we can calculate the max of these two quantities, which is the below quantity, which is delta 1 of bias times the transition from bias to bias, and we multiply it with the emission probability of observing a H head from a bias coin. So this turns out to be 0.42 times 0.9 times 0.7, right? What is psi2 of bias? Psi2 of bias is the state which maximizes this quantity. So the state at the previous iteration, that is, so the state of the previous iteration which maximizes this quantity is bias, right? Thus, we can write delta 2 of bias as bias, and we're showing the argmax operator in play here. Similarly, could you take a minute and calculate delta 2 of fair and psi2 of fair? Okay, so in terms of delta 2 of fair, it's a maximum over these two quantities. First, you start in the fair state and you observe this the first observation x1. Delta 1 is responsible for these two joint probability. You take a transition from fair to fair, or you start in state bias and observe the first observation x1, and then you make a transition from the bias to the fair. You want to see which of these two paths is most likely. It's clearly the path from fair to fair which is more likely, given that the transition probability from fair to fair is significantly dominating the transition probability from bias to fair. Thus, phi to fair is fair, and if we calculate this whole quantity, it will come out to be 0.09, right? So let's just write down these two numbers, delta 2 of bias and delta 2 of fair, and write down the two individual psi's for bias and fair at time t2. And can you take a minute and similarly now calculate delta 3 of bias and delta 3 of fair? Okay, assuming that you have now completed the calculation, I'll show you the answers. Delta 3 of bias is the max over starting, not starting, so of being in state 2 and being at time t2, being in the bias state and having observed the first two observations, then making a transition from bias state to the bias state, or being in state fair at time t2 and having observed the first two observations. Both of these are in the quantity delta 2 and multiplied with making a transition from fair to bias. So if we look at plug in all the values for delta 2 of bias and the transition from bias to bias, fair to fair, and the delta 2 of fair, it turns out that delta psi 3 of bias is significantly greater in this case. So the psi 3 of bias is biased because amongst these two quantities, the quantity corresponding to bias is higher. And if we calculate delta 3 of bias, it turns out to be 0.167 approximately. We can do the same calculation for delta 3 of fair, and it will turn out to be 0.0405, and psi 3 of fair will turn out to be fair. Right? So now we have all the required quantities, right? So we have delta 1 of bias as 0.42, delta 1 of fair as 0.2. Similarly, we have delta 2 of bias fair and delta 3 of bias and fair. We also know psi 2 of bias, psi 2 of fair, and psi 3 of bias and psi 3 of fair. So we can then calculate Z3 star, which is what is the most likely final state, or ZT star. So if we go back, we calculated ZT star as the argmax of delta T of I, right? So capital T is the last timestamp. So in our example, capital T is 3. Now, what do you think is the argmax of delta 3 of bias versus delta 3 of fair? The quantity which maximizes, or the state which maximizes delta 3 over all I is bias. Right? So delta 3, so Z3 star is argmax over these two quantities, delta 3 of bias and delta 3 of fair, and thus it is bias, right? And using the recurrence backtracking procedure that we, sorry, not the recurrence, the backtracking procedure that we mentioned before, we can now easily calculate the most likely path. So what we said is the most likely final state is bias, right? But what was the most likely path to, or the most likely path previous step to reach Z3 star equal to bias? So that was psi 3 of bias, which is bias, and thus Z2 star is Z3 is psi 3 of bias and bias. And similarly, if we go one step before, we can calculate Z1 star as psi 2 of Z2 star, which will turn out to be bias, right? So thus we can compute Z star to be bias, 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 which in our case is the same as MPM, but we've seen an example before, of a trivial example before, where map and MPM solution may not be consistent. So we have now thus far covered a few important problems in HMMs. Now in the next video, we'll go towards the final and the sort of the hardest problem in HMMs, which is how do we do the parameter learning? How do we learn theta equal to pi AB?